Broadcast is now starting. All attendees are in listen-only mode.
Welcome, everyone. Thanks for joining us today. I'm Kelly Pirtle with NOAA Communications in Norman, Oklahoma, and I'm a member of NOAA's Central Region Collaboration Team. I'm your host for today's webinar. Today's 3-minute thesis webinar has been organized by the NOAA Central and West Regional Collaboration Teams to share information about NOAA's role before, during, and after wildfire events. This is a very timely topic, with large wildfires currently burning in many locations in the northwestern U.S. and smoke recently moving across the country all the way to the northeast. According to the National Interagency Fire Center, there are 82 large fires raging as of today, with a total of 1.7 million acres burned by those fires. For this entire year, a total of 3.4 million acres have been burned across the United States. I hope you will enjoy this webinar format, which is based on a model used by universities across the country as a way to briefly share information about a project, initiative, or research. Each of today's panelists will have 3 minutes and 1 slide to cover their topic. You can see from the outline we have a variety of topics, and after each group, we will take a break for questions from you, our audience. And at the end, we will have a few minutes for all panelists to respond to your questions. At any point during the presentations, please submit your questions in writing using the questions pane of the GoToWebinar panel. We are recording today's webinar, and it will be posted Monday on our homepage, www.noaa.gov/centralregion. We would love to get your feedback on this event. Please take a moment at the conclusion of today's webinar to complete a very brief survey. Before we get started, I'd like to thank the NOAA West and Central Regional Collaboration Team coordinators, Asia Shumalo, and Bethany Perry for their work putting together this excellent lineup and coordinating this webinar. Asia will be taking your questions and sharing them with our presenters. I'd also like to thank the many NOAA employees involved in wildfire events, either as part of their job or as volunteer wildland firefighters. We are proud to highlight today a few of the many ways NOAA serves our country through science, service, and stewardship. All right, we're going to start our webinar with an overview of NOAA's role in wildland fires presented by Robyn Heffernan. She is the NOAA National Weather Service Fire Weather Science and Dissemination Meteorologist located at the National Interagency Fire Center in Boise, Idaho. Since early 2011, Robyn has been responsible for leading several technological and science-based efforts for the National Weather Service Fire Weather Program, as well as integrating these efforts into fire weather operations. She currently serves as chair of the National Wildfire Coordinating Group Fire Environment Committee. Robyn, take it away.
Great, thank you, Kelly. So good afternoon or good morning, whatever it might be for you. I want to thank you today for your interest in NOAA's efforts to support the wildland fire community. As you probably know, weather is a key element to fire occurrence, fire behavior, and fire growth. It is for this reason that NOAA has teamed together through the National Weather Service, the Office of Oceanic and Atmospheric Research, and the National Environmental Satellite Data and Information Service, all working together as one NOAA to provide fire weather products and services to our wildland fire partners. These products and services are developed based on the decisions that our wildland fire partners need to make. We start first with these decisions, and then we work backward to determine what fire weather information is needed to inform those decisions, the data required, and the research and development needed to inform the entire process. As you can see by this graphic, NOAA supports each and every phase of the fire life cycle, and we do this with product and service development through the process I just mentioned. NOAA fire support starts long before the fire does, with partnerships starting with our local fire departments, up through the geographic area coordinating centers, and to the national level at the National Interagency Fire Center in Boise, Idaho. Equally important are our partnerships with NGOs, academia, research consortia, and the media. We all work together with one mission of safety and wildland fire management. As we look at the fire life cycle, NOAA's specific support begins with monitoring. This is on the left in gray, and monitoring of drought and field conditions, climate assessments, and looking forward through seasonal outlooks, all of which to help determine the timing and severity of anticipated fire activity. Pre-ignition support is in orange. It combines fuel and weather conditions to provide fire weather forecasts, site-specific spot forecasts, and hazard products such as fire weather watches and red flag warning. These hazard products inform users that if a fire ignites in the warning environment, it will likely grow large quickly and become a safety concern. Or it's possible a warning could be issued for the possibility of multiple new fire starts due to excessive lightning. Detection in brown support utilizes the latest technology of polar and geostationary satellite imagery to detect fire start, monitor radiative power, and fire growth. This imagery is truly a game changer with regard to fire intelligence information. We can see fires like never before. Wildfire forecasting in red, our support for forecasting, incorporates the latest technology with regard to fire atmosphere coupled modeling and smoke modeling, and making these tools available to our incident meteorologists on the ground who work at the fire location hand in hand with the incident management team to inform all the decisions they make on the fire. Finally, post-fire support in blue utilizes the latest remote sensing technology to map burn scars, so forecasters can monitor these areas for potential heavy rainfall and warn of deadly debris flows. This is just a quick overview of NOAA's multifaceted approach to support wildland fire efforts from an atmospheric science perspective. Thank you.
Thank you so much, Robyn. Our next presenter is Matt Elliott, the Warning Coordination Meteorologist at the National Weather Service Storm Prediction Center in Norman, Oklahoma. Matt is no stranger to fire weather, having grown up in Northern California and spending 15 years in Oklahoma. He will discuss fire weather outlooks, the role of the NOAA Storm Prediction Center, by highlighting fire weather events near his hometown in California. Go ahead, Matt.
Thanks, Kelly, and thank you everyone for being here today. The National Weather Service's Storm Prediction Center has been issuing daily fire weather outlooks across the contiguous United States since the late 1990s. The outlooks highlight areas where pre-existing field conditions combined with forecast weather conditions during the next 1 to 8 days will result in a significant threat for the ignition and our spread of wildfires. Fire weather conditions include the combination of strong winds and low relative humidity with risks of elevated, critical, and extremely critical. The Kincaid fire in Sonoma County, California, started in an area of critical fire weather conditions. One of the first questions an incident commander may have is, what are the forecast fire weather conditions over the next several days? In this case, conditions were expected to decrease initially, but the Storm Prediction Center was already forecasting the possibility of higher-end critical fire weather conditions in 5 days. 2 days prior to the event, extremely critical fire weather conditions were forecast, and by the day of the event, the SPC forecast stated that dangerous fire weather conditions were likely. And this outlook was well coordinated with the message and the red flag warning from the National Weather Service Forecast Office in Monterey of a long duration and historic event. And these ended up being excellent forecasts with a measured wind gust of 103 miles per hour near the fire and a doubling in fire size. And forecasts of fire weather conditions well in advance of an event, as in this case, can help inform difficult evacuation decisions and help incident commanders better manage resources. Fire weather also includes isolated to scattered dry thunderstorms, which are thunderstorms where little to no precipitation reaches the surface and lightning ignitions are possible. Dry thunderstorms are a logistical challenge for fire operations, as they are often difficult to forecast and can start many new wildfires. This is a photo I took in the Central Valley of California of fire trucks driving north towards thunderstorms in the distance. This particular unit is CAL FIRE San Mateo Santa Cruz. They have likely traveled from their station in the South Bay of San Francisco along the Pink Line and are headed toward the threat for dry thunderstorms is greatest, as shown by the isolated dry thunderstorm area that the Storm Prediction Center had been forecasting for several days. For perspective, it's a 4-hour drive just to reach the edge of the threat area, and in many cases, it can take several days for resources to pre-position ahead of an event, which is why it is vital to provide accurate, reliable forecast information as far in advance as possible so that resources can be best positioned to provide initial attack on new ignitions. The Storm Prediction Center fire weather outlooks are used by the National Weather Service and other federal, state, and local government agencies and wildfire partners. And alongside forecasts and warnings from local National Weather Service forecast offices and support from incident field meteorologists, the Storm Prediction Center outlooks can provide critical information on the forecast weather component of wildland fire. Thank you.
Thank you, Matt, for sharing a role of the Storm Prediction Center that maybe some were not as familiar with. Have you ever wondered what it's like to be part of the fire response team? Our next speaker, Dan Borsum, can certainly tell you all about it. As an incident meteorologist, or IMET, with the National Weather Service Forecast Office in Billings, Montana, Dan just returned Monday from an assignment on the Beaverhead Deer Lodge Forest in southwest Montana. This was the 58th time he has been deployed as an IMET. In addition, Dan is part of a cadre of field employees who lead training efforts to ensure the National Weather Service cultivates and maintains a group of volunteers who can meet the weather needs of incident management teams who respond to wildfires across the West. His presentation on the role of a National Weather Service incident meteorologist will give you a glimpse into the fast-paced, ever-changing, and multifaceted service IMET strive to provide in the dynamic wildfire environment. Dan?
Thanks, Kelly, and thanks everybody for giving me a chance to talk today about the IMET role in wildfire. In a field that involves uncertainty, I thrive in an environment that is unpredictable. I'm excited by the unexpected and the challenge to bring coherency to what others see as chaos. That is what I relish about being an incident meteorologist, or IMET. As a backdrop to my talk, I'm using this picture taken Sunday night by IMET Corey Motice. And this image really is a metaphor for the daunting challenges that IMETs repeatedly face. An IMET walks into an environment in which nothing is certain. The organizational structure, the work environment, living arrangements, all these things change from assignment to assignment and even day to day within the same assignment. And all of this in the face of the fact that we are challenged to try and bring clarity to the most variable element of wildland fire, the weather. So what does an IMET do? Everything. IMETs leverage NOAA's tools to bring tactical and strategic guidance to firefighters. And those two words are deliberate, strategic and tactical. That means as an IMET, I'm responsible for knowing what's happened 60 days in the past and what will happen 60 days in the future, and what's going to happen next week on an hourly basis, and what's happening right now up to the minute. So in the next 90 seconds, I'm going to blast through some of the hows and whys and whats that we do when we're out there on assignments. First of all, we maintain a state of readiness so we can be anywhere in the country on 24 hours notice and make it seem like we've lived there all our lives as we talk knowledgeably about the weather. We maintain a constant weather watch to keep firefighters out of harm's way. And this involves more than just using satellite and radar information, but also being embedded with the incident management team and knowing the types of resources out there and the locations that they're working to determine specific risks and exposures. We work alongside fire behavior analysts, long-term analysts, and other team members to fuse weather projections with fuels data and fire activity information to run models which are going to predict fire intensity and fire growth. A very important skill is to be able to identify wind flow patterns through the terrain and run specialized wind models to help develop a conceptual picture of what it looks like in that landscape on a 200-meter basis. Our training includes the ability to site portable weather stations and launch mobile radiosonde upper air balloons to enhance our knowledge of the weather patterns across a local fire area. We attend public meetings and speak knowledgeably of the climatic challenges a community may face, showing empathy that their multi-month precipitation deficit has led to the fire severity that is forcing them from their homes. And all these above activities are done with constant communication with multiple Weather Service forecast offices, people in field and national and regional offices, and meteorologists from predictive services to ensure that the firefighter on the ground is getting one coherent message about the weather. This talk would not be complete unless I acknowledge the support of the weather offices across the country, which are providing background support, giving us information to make us look smart out there and keeping us and our firefighters safe when we do finally catch a rest at night. And it's the whole of NOAA that is the thrust of the spear. The IMET is just really the tip. Thank you for listening.
Thank you, Dan. It is such an important role that the IMETs play. We will now take a few minutes to address some of the questions submitted from the audience. So our previous two speakers will join us, as well as Asia Shumalo, I got it right this time, who will be taking your questions and coordinating the questions part. Thanks.
Thanks, Kelly. So the first question is for Robyn. What are NOAA's future plans to help combat the ever-growing wildfire problem?
Thank you, Asia. Well, that is the question of the day, right? For not just NOAA, but for all government agencies. In NOAA, though, we are teaming up together, like I mentioned at the beginning of my talk, all together as one NOAA through Office of Atmospheric Research, Weather Service, and NESDIS for satellite and data imagery. And we are collaborating under a new group called FOREST, the Fire Observation Research and Service Team under the Water, Weather, and Climate Board to be able to respond to this ever-growing need for wildland fire support. So this is a group under NOAA that's going to be new to respond to that. And then, of course, we're going to participate in any of the new multifaceted government federal teams that are going to be put together to work on this effort as well.
Thank you, Robyn. The next question is for Dan. Does the Storm Prediction Center monitor and forecast pyroconvection on active fires? Excuse me, that was for Matt. I'm so sorry.
We don't specifically do pyroconvection, but we do dry thunderstorms. And certainly we might highlight areas and mention in the text plume-dominated thunderstorms, but we specifically don't outline for fire-specific areas in our outlooks. There are more regional outlooks for larger areas. That'd be more for the weather forecast offices.
Thank you, Matt. And this next one is actually for Dan. So given that your work can require 2 weeks straight out in the field with 16-hour days, all while sleeping in tents, what gets you out of your sleeping bag in the morning?
Just the knowledge that there may be an 18-year-old kid who's going to have his face in the dirt all day long, and there could be something changing in the sky that he's really not aware of. So maybe something I say that morning during the morning briefing causes him to sense something during the day that makes his hair stand up on the back of his neck. And he takes a step back, looks at the situation, and reevaluates his safety parameters and makes a good decision that could possibly save his life.
Thank you. I appreciate that. I've got a couple more questions. I'll go back to one that came in from Matt. How does the Storm Prediction Center coordinate with National Weather Service forecast offices, other federal agencies, and external partners when forecasting fire weather conditions?
Yeah, absolutely. The Storm Prediction Center works very closely with the local National Weather Service forecast offices, other federal agencies, and the external partners. And part of this includes daily coordination calls with the national and regional coordination centers, and also internal collaboration with the local National Weather Service forecast offices. You know, I think Robyn and Dan hit it really well. The fire weather forecasting really is a team effort. You know, we're all working together in local and regional knowledge of things like current fuel status, fuel types, terrain features, among many other things, really are essential parts of fire weather forecasting. So without working with everybody, you really don't have a complete picture of that fire environment.
Great, thank you. And we'll do one more. So this one is for Dan. Is there a way to incorporate on-scene fire behavior like single tree touching to the weather patterns in that area?
There is a lot of effort that goes to be monitoring the situation on the ground. We're watching it, and then we go back to previous weather patterns. We go back to previous fire scars in fire history to correlate what the weather has done in that area for previous fires. And that's a fusion between my role with the fire behavior analyst, hand in hand, to take historical fire knowledge, look at weather projections, and try and correlate, because it helps paint a picture in a firefighter's mind as to some experience that they've seen before, how that means they're going to be seeing conditions evolve during the day ahead.
Thank you for that, Dan. And with that, thank you all for the great questions. And Kelly, I'll turn it over back to you.
All right, thank you, Asia. This is so informative, don't you all agree? Remember, you can type your questions in the questions pane of the GoToWebinar control panel. We'll now transition to our next group of presenters. Satellites are a useful tool for identifying wildfire locations, and we're going to learn more about that from Dr. Wilfred Schroeder, a physical scientist with the Satellite Analysis Branch of NOAA's National Environmental Satellite Data and Information Service, NESDIS, located in College Park, Maryland. He has more than 20 years of experience in satellite-based fire detection and has been directly involved in the development and validation of operational products serving both fire management and air quality communities. Wilfred will share information about the Hazard Mapping System Fire and Smoke product. Wilfred?
Thank you, Kelly. So routine satellite-based fire detection and smoke mapping information derived from the same type of imagery that we just saw is available through the Hazard Mapping System, which is maintained by the Satellite Analysis Branch located in College Park, Maryland. This system integrates high-frequency observations from geostationary satellites and higher spatial resolution data from polar optic satellites to create a daily map of fire locations and smoke plumes for all of North America and neighboring areas in Central America and the Caribbean, in addition to Hawaii. A team of fire analysts interrogate the near real-time satellite data, correcting for any potential false alarms and omission errors in the automated fire products before releasing that information to the public. For example, fire detections originated from gas flaring activity are screened out, and small or low-intensity fires omitted by the automated products are added to the database. Fires are described as point locations representing pixel center coordinates, and therefore can be composed of a single point on the map or a large cluster of points representing major wildfires. Fire radiative power, which can serve as a proxy for fire intensity, is also available for most detections. Smoke mapping, on the other hand, is based on visual image interpretation and is often corroborated by air quality products and observations. Smoke plumes are labeled as either light, medium, or heavy density based on their optical thickness. The fire and smoke analyses are performed 24/7 and year-round, with public-facing information being updated several times a day as new data become available. This resulting quality control, fire location, and smoke data are made available via NAWIPS, in addition to GIS-friendly formats for using downstream applications, including strategic wildfire management and air quality modeling. The fire and smoke data are also accessible to the general public through the Hazard Mapping System webpage and are particularly popular during the peak fire season when fires and smoke can affect millions of people and across multiple states. Back to you, Kelly. Thank you.
Thank you, Wilfred. Next, we'll hear from Eric James. He is a senior research associate at CERES, the Cooperative Institute for Research in Environmental Sciences at the University of Colorado, where he works within the NOAA Global Systems Lab in Boulder, Colorado. His research interests include rapidly updating numerical weather prediction, observation impacts within NWP, and applications such as renewable energy forecasting and flash flood prediction. Eric is a key member of the team that developed the HRRR-Smoke model, and he will share how it predicts the evolution of wildfire smoke plumes. Eric, tell us more.
All right, thanks, Kelly. So the HRRR-Smoke is the first operational numerical weather prediction in the US that is fully coupled between meteorology and smoke. So it's an exciting development. So the starting point for the HRRR-Smoke is satellite fire detection, as Wilfred just described. So we use satellite fire detections from 4 polar orbiting satellites currently using the VIIRS and MODIS instruments aboard those satellites. And we use the satellite detected fire radiative power to parameterize plume rise from wildfires and also the emission, the actual amount of smoke that's emitted, the biomass burning emissions. We cluster the satellite fire detections onto the model grids. So we run a 13-kilometer domain, which covers all of North America, and we run 2 3-kilometer domains over the lower 48 United States and over Alaska. And at that point, we can inject a smoke tracer into the model 3D atmosphere, and then the model physics and dynamics will predict the spread of the wildfire smoke on a national scale. So there's many important applications for these forecasts. First and foremost, smoke pollution is a major concern. This example on the bottom left here shows a case from September of 2018, when there was a prescribed fire in northern Idaho that sent a lot of smoke into the Missoula area, and it impacted outdoor activities on this Friday evening. And you can see the observations of the air quality there on the bottom. The HRRR-Smoke was able to capture the spread of the smoke plume into the populated area in this case. Another important application is surface visibility forecasts. There's been a number of accidents in the last few years related to low visibility due to smoke. This plot with the blue and red curves shows verification of surface visibility forecasts, less than 10 miles visibility, showing the critical success index from a version of the HRRR without smoke, shown in the blue, and then including the smoke impact in the red. And you can see the skill scores are higher when we include the impact of smoke on visibility. And then finally, another important forecast impact, which we've seen in recent days even, is the impact on surface temperatures. When you have a thick smoke plume, the surface temperatures will be reduced during the daytime. And we can actually capture this effect with the HRRR-Smoke. This example on the bottom is again from Missoula, Montana. It shows a case where there was a thick smoke plume restricting the surface heating from the sun. And when we include that effect in the model, we can get a much more accurate prediction of cooler surface temperatures during the daytime due to the smoke plume. So in summary, the HRRR-Smoke is a really important baseline forecast product for evaluating new smoke models in the future as we develop the next generation of coupled air quality models. Thanks for your interest.
Thank you, Eric. It's so interesting to hear about how HRRR-Smoke is being used. Our third speaker in this group is Joshua Schwarz, who goes by Shuka. He is a research physicist in the Chemical Sciences Laboratory of NOAA Research located in Boulder, Colorado. He was one of 4 mission scientists from NOAA and NASA who coordinated a major field campaign focused on fire that took place in 2019 called Fire Influence on Regional to Global Environments and Air Quality, but really known as FIREX-AQ. He will share how FIREX-AQ science strengthens the foundation for NOAA operations. Joshua?
Thanks, Kelly. Great, thanks. We've just heard about some of NOAA's tremendous operational capabilities with respect to wildfires, and specifically a smoke model and satellite observations. I'd like to draw out the connection from these day in and day out services to the nation and the kind of work that we focus on in the Chemical Sciences Laboratory, namely basic research on the atmosphere. I'll highlight a less regular activity, field research, and I'll focus on the FIREX-AQ campaign of 2019 to paint a line from the field to improved understanding and then on to improved services. The blue arrow towards the top of this slide indicates this progression. For an example of this within FIREX, I'll focus on progress with a single measurement from satellites that is widely used in models. FIREX-AQ coordinated 4 research aircraft, a handful of mobile laboratories, and multiple ground sites to study smoke emissions from wild and intentional fires. During the mission, we partnered with state and federal agencies, private companies, and universities to make the most detailed and extensive measurements that we possibly could. In panel 1 of the slide, you can see a few of the planes that we used to collect some of the same information that is routinely collected on global scale by satellites. From each of these platforms, the energy released by fires was directly measured via a parameter called the fire rate of power, or FRP, which you can see is visualized by a camera flying over a fire at the bottom of the panel. And this looks a lot like a satellite picture that Wilfred just showed you. FRP measured by satellites is a wonderful asset because it can be used to estimate the emissions from fires over the whole world. But our ability to use satellite FRP is limited by how good those estimates are presently. And frankly, they aren't good enough yet. For this reason, we also measured FRP from the aircraft, different heights above the ground and with different resolution than possible with the satellites, to build an exceptionally strong record of FRP for just a few fires. Further, we made comprehensive measurements of the smoke coming out of those same fires, not only the amount of smoke, but also its composition, the details of the particles and gases that make up the smoke, as well as the way those components change in the air with sunlight, temperature, humidity, altitude, and so on. I've just described the work necessary to collect a lot of interrelated data focused on FRP. The next step in the process is to learn something from that data. That's what I tried to show in panel 2. Here you can see a relationship in the top graph observed between FRP and smoke emission rates, which were developed by combining measurements of smoke at the airplane with remote sensing of the extent of the smoke plume, which you can see in the animation at the bottom. This kind of analysis, which can be taken much further than shown here, provides advances in basic understanding. Finally, in panel 3, I tried to show that this kind of information can filter up into increasingly complex models. First, it can feed the models that try to estimate the amount of smoke from fires, namely emission models. In turn, that information will improve higher level models like HRRR-Smoke, and I'm sure you recognize the source of this forecast at the bottom of the panel 3 at this point. You can imagine how our data set can be used to add realism to models with time. Ultimately, our research supports better services to the nation. Thank you.
Thank you, Chuka. Would you like to, you have an interesting background. Would you like to share with us where you are?
Sure. I'm at Ellington Field in Houston at a NASA operations center where we have a research aircraft. That's the WB-57 high altitude research aircraft. We're going to be starting to make some stratospheric measurements in a short while. So this is test flights and getting ready. I hope you enjoy the view.
Yes, very much. Thank you. Thank you. All right, I'll turn it over to Asia for some questions. Remember to submit your questions in the questions pane of the GoToWebinar control panel. Asia?
Thanks. And Chuka, can you come back on the screen too? So the first question is for Wilfred. What satellite products and AWIPs do you recommend for fire and smoke monitoring?
That's a good question. So it really depends on the type of application, on the purpose of your data usage. So for real-time response, the GOES satellite, the GOES ABI fire data information would likely be your best option. For more spatially explicit fire information, views will be the one data set to recommend. So it really depends on the time scale, on the spatial scale that you're looking at. But usually for high frequency observation or quick turnaround, GOES data would be the go-to the data set, whereas for more spatially explicit and more spatially refined information, views would be the primary data to work with.
Thank you. The next question is for Eric. Does the methodology and data availability differ when the fire originates in Canada?
Yeah, that's a good question. So if the fire is outside of the HRRR domain, which is the 3-kilometer domain that covers the lower 48 US states, then it'll be initialized in the 13-kilometer grid spacing rapid refresh model. The approach is exactly the same. It's just that the model grid spacing is larger, and once it's emitted and the smoke plume is predicted in the RAP model, if it comes into the HRRR domain during the forecast, that will be handled through the lateral boundary conditions for the HRRR model. So it will be captured eventually within the HRRR through the lateral boundaries.
Thank you for that. For Chuka, you claimed that emissions inventories aren't perfect. What's wrong with them?
Well, no one's perfect, nothing's perfect, but the emission inventories can be improved. I think that's the bottom line. One of the issues is that if you use something like FRP that's measured by satellites, satellites aren't necessarily always overhead when fires are occurring. If you look at NOAA's new generation of satellites, GOES East and GOES West, those are geostationary, but they don't actually image the whole globe. So the satellites that image the whole globe pass over once or twice a day, and they can't account for all the fires. Also, small fires or fires in underbrush are hard to detect. So building a emissions inventory out of FRP is not trivial.
Thank you for that. And the last question I think all of you might be able to contribute to, have any of your models started to experiment with AI algorithms?
Sorry, go ahead, sure.
But we've used AI a little bit for instrument data analysis, and I'd say that's a developing and exciting topic that probably also has some limitations.
And I welcome either of you to chime in with your experiences as well.
Yeah, I can say a few words. Yeah, AI is being tested extensively with active fire detection. So yeah, this is an area that is expanding very quickly, and we are looking very closely at the options available. Yes.
I would say for the numerical weather prediction aspect, there's a lot of different applications for machine learning. One of the ones that has received the most attention is in physics parameterizations, being able to use machine learning to get more accurate parameterizations to resolve things that you cannot capture on explicitly on the model grid. So that's one area where in numerical weather prediction, we're moving towards more machine learning.
Great, thank you. And thanks for all those great questions, audience. And with that, I'll turn it back to Kelly.
Thanks, Asia. I'm enjoying this so much. How about you all? We now begin our final group of speakers. Brett Lutz is a lead forecaster, fire weather program lead, and incident meteorologist at the Medford, Oregon National Weather Service Forecast Office. He will be deploying as an IMET to the large bootleg fire in Southern Oregon, I think later today, or this weekend at least. Today, he will share with us some of the many ways wildfires affect people and their communities. Brett?
Thanks, Kelly. So in early September of 2020, during an unusually dry summer, a rare severe east wind event combined with human-caused fire starts, resulting in a historic period of catastrophic wildfires and smoke, occurred across the western United States. These wildfires and thick smoke had major impacts on western communities that were already coping with challenges related to COVID-19. Leading up to the wind event, NOAA's National Weather Service Western offices and the Storm Prediction Center issued strongly worded watches and warnings regarding weather-related fire spread concerns from the expected strong, dry wind event to prepare core partners and the public for potentially significant wildfire. This was messaged via social media and numerous calls and webinars with partner agencies. Throughout the event, NOAA's National Weather Service amplified partner messaging regarding awareness, preparedness, and evacuation information. During the 2020 fire season alone in the states of California and Oregon combined, over 12,000 fires burned, scorching over 5.6 million acres, destroying over 13,000 buildings, many of them homes, as you see here in the Alameda fire graphic, and sadly, also resulting in 44 deaths. Critical power and roadway infrastructure was disrupted for days to weeks, even in areas that survived the fires. The public, state, and federal employees were adversely affected due to being evacuated themselves or sheltering those who had been evacuated, some of whom had lost everything. NOAA's National Weather Service served as a critical information point regarding expected weather affecting fire spread and containment, air quality, and cleanup efforts led by the Red Cross and FEMA. In addition to weather forecasts protecting life and property, NOAA's National Weather Service coordinates and collaborates with state agencies regarding air quality alerts for wildfire smoke. State, federal, and public air quality monitors and smoke models, particularly the HRRR-Smoke model, are used in generating general smoke forecasts for the public. More detailed smoke concentration and visibility forecasts are made by the National Weather Service for aircraft fighting wildfires and for countless outdoor events. Having had wildfires tear through one's community leaves long-lasting physical and emotional scars that need to be healed. NOAA's National Weather Service has been evolving to help this healing process by preparing people for the changes of tomorrow and beyond, because coping with wildfire in a changing climate is something that many Westerners must now be mindful of year-round. Thank you for joining us today.
Thank you, Brett, for reminding us of the many ways people are affected by fires. Shifting gears slightly, have you ever wondered what drought has to do with wildfires? Britt Parker will answer that question and more as she shares information about drought and wildfire interaction. She works with NOAA's National Integrated Drought Information System, also known as NIDIS, in Boulder, Colorado, as an employee of the Cooperative Institute for Research in Environmental Sciences, or CIRES. Britt serves as the Drought Information Coordinator for the Pacific Northwest and Missouri River Basin Drought Early Warning Systems. She also oversees the NIDIS Drought and Wildland Fire Nexus Strategy. Take it away, Britt.
Thank you so much. So drought is a common climate phenomenon that impacts wildfire planning, fire behavior, fire effects, and subsequently wildland fire management overall. While local weather drives day-to-day fire activity, seasonal climate enables wildfire through wet periods that generate vegetation growth and dry periods that cure that same vegetation into flammable fuels. The physical relationship between drought and fire is complex given the many and varied first and second order effects. Wildland fire managers, fire meteorologists, and fire behavior analysts have an increasing need for drought information to be incorporated into fire-related forecasts and long-term fuel management planning. The Western Regional Climate Center, the Desert Research Institute, and the National Integrated Drought Information System partnered to form the NIDIS Drought and Wildland Fire Nexus, or NDON. NDON is both a strategy and a network. As a strategy, it promotes meaningful consultation with the wildfire management community to identify gaps in information and work through a co-production model to address those needs. NDON also functions to establish a robust drought and wildland fire decision support information network at multiple scales, from sub-regional to national. Under NDON, NIDIS partners in applied research projects under a number of topic areas seen on this slide. Recent and ongoing research projects include incorporating drought information into the National Fire Danger Rating System. This includes the development of an automated system to generate subseasonal forecasts of fire danger indices and relative fire risk metrics. And the examination of the relationship between common drought indices, such as the Evaporative Demand Drought Index and an FDRS outputs, to inform integration of drought indices into the rating system. An exploration of the interactions of drought, wildfire, and heat waves, as well as work to quantify the complex interactions and feedback between fires, drought, and snowpack in the western U.S. to improve prediction. The exploration of how drought and vegetation recovery influences post-wildfire hazards, including debris flows and shallow landslides, and whether this influence can be modeled to inform rainfall intensity duration thresholds through time. Work to build our understanding of how fuel flammability responds to evaporative demand, and if short-term evaporative demand creates tipping points for fuel flammability. And finally, an examination of the climate, weather, fire timeline, starting with antecedent conditions through fire on the ground to improve our understanding of climate and weather temporal influences on fire across regions. Continued engagement and knowledge exchange with partners such as the Geographic Area Coordination Centers, Predictive Services, the National Weather Service, and other federal and state agencies, as well as prescribed fire councils and alliances, ensure the outcomes of this work are integrated and utilized in fire management decisions. Thank you.
Thank you, Britt. The understanding drought is just so important. Last year, more than 10 million acres burned in the U.S., with more than 600,000 in Colorado alone. The monsoon that failed to develop last year has come back to Colorado this year and has brought with it new problems across the state. Flash flooding, mudslides, and debris flows causing interstate closures and, unfortunately, loss of life. Just last night, the Grand Junction Forecast Office issued a flash flood emergency for I-70 and the areas affected by the Grizzly Creek fire. The interstate was closed by flash flooding, and last we checked, it still is. Tony Anderson, our final speaker, is the service hydrologist at the National Weather Service Forecast Office in Pueblo, Colorado. He began working in post-fire hydrology when he moved to Pueblo in 2015. He's also the deputy chair of the National Weather Service Post-Fire Hydrology Working Group. Tony told us the incident isn't over when the fire is out, and we thought that was the perfect title for his presentation. Tell us more, Tony.
Thank you very much. And I appreciate the opportunity to share this subject with you. Wildfires affect the land, its residents, and the National Weather Service long after the flames are out. High-intensity fires change almost every aspect of the hydrologic regime. For residents of the area, this can mean unfamiliar risks to their lives and property. Flash flooding and debris flows are common after wildfires and can be particularly dangerous. In 2018, heavy rain hit a burned area above Montecito, California, and generated a debris flow. Despite accurate and timely warnings and evacuation orders, 23 people were killed and hundreds of homes destroyed. This heightened risk of flooding and debris flows can last for years. Fires can remove vegetation and alter soils to create a perfect storm of runoff. Flash flooding is the most common hazard in this environment. A small stream south of Pueblo, Colorado, was affected by a wildfire. The creek was small, about 4 to 5 feet wide and maybe 6 inches deep. No one we interviewed remembered it flooding. A year after the fire, a storm dropped nearly an inch of rain on the area in about 15 minutes. The resultant flood was estimated by video to be 80 feet wide, 2 to 4 feet deep, and was moving 10 feet per second. Standing waves at least 2 feet high were seen in the middle of the channel. Under the right conditions, the rapid runoff can mobilize material from the hill slopes and the channels and become a debris flow. Debris flows are mostly solid material and can move faster and build themselves higher than a flash flood. If you can imagine the power of a 5,000-pound boulder moving at about 30 miles per hour. While flash flooding is more common, the debris flow is the more inherently dangerous phenomenon. The National Weather Service begins working while the fires are still burning. We work to protect the firefighters and then to assess the fire and identify the hazards and risks. This is often in cooperation with the burned area emergency response teams that are deployed for that purpose. Our next step is to educate our partners, the public, and ourselves of the new hazards and how we are working to address them. Operationally, the post-fire environment has an impact out of proportion to its size. In 2019, burn scars represented less than 1% of Pueblo's area of responsibility, but resulted in over half their flash flood warnings. Small areas must be closely monitored whenever it is raining nearby. 5 minutes of rain is enough to change a creek into a torrent or into a wall of rock and mud, and to change lives forever. Thanks.
Thank you, Tony. We're so fortunate that you and others are monitoring these burn scars and helping save lives. It's now time for questions about this last group. What questions do you have for these presenters, Asia?
Okay, thanks, Kelly. The first question is for Brett, and it's about defensible space. So the questioner asks, we keep our grass short near our home, but cannot water it due to being on a cistern. Is this a major problem for protecting our space?
I think the most important part is that you're keeping your grass short because that reduces the potential flame lengths that you could have from a fire that would move through. Of course, it's also important to make sure that your trees are trimmed back from your property, from your home, so that you don't get ash fall or embers on the roof. But of course, if you could water, that would be helpful. There are, some people have emergency watering systems should a wildfire show up, and they have a holding tank that they keep the water in just in case, especially if you're in a rural property that's not going to see protection very fast if a fire starts.
Thank you for that. The next question is for Britt. Britt, can you discuss the role of social science and/or user engagement in the end-on strategy?
Yeah, that's something that we work very closely with partners like the Western Regional Climate Center and some of our NOAA RESAs on, and some of the projects they've been involved in are really in kind of better understanding, working with the Weather Service, the red flag warning system, and some of how that information, when it hits the public, is understood. And we're also looking, as a lot of our research projects are getting to the point where we do have results and outcomes, in how social science and communication can be used and harnessed to engage with our drought early warning systems regionally to deliver information on things like the benefit of prescribed burns and issues such as that, in partnering with all of our partners.
Great, thank you. And that was a great segue to our next question, which is for Tony. The questioner asked, putting fires out for the past 200 years is causing larger and hotter fires today. How can NOAA help promote the use of prescribed burns?
That's a great question. It's a little out of my wheelhouse.
Maybe any of you.
What I can say is, if we can reduce the fuel loads, we can reduce some of the impact of high intensity fires. Fire is a natural thing. The high intensity fires have high intensity impacts. And if we can reduce that, we can reduce some of the post-fire, some of the intensity of the post-fire impacts that we're seeing. So we can, from my perspective, our best approach is to help people understand the benefit of those prescribed fires and the fuel reduction that they entail.
Great. Sorry to put you on the spot with this one. This next one is more truly for you. Are burn areas monitored for vegetation recovery and decrease in flood risk?
We're trying very hard. It's a science that is not well developed at this time. I was just approached this week about joining a study in that regard. People are trying to monitor it. They're trying to use remote sensing, satellites, aircraft, but right now, making the connection between vegetation recovery and hydrologic recovery, the science, as far as I know, is just not there yet.
Thank you for that. And so with the time we're at right now, I'd like to welcome all of our panelists back on the screen, and I'll start working through the questions that our listeners offered up to you guys. So I'll start at the end. I'll kind of hop around to drag you all in.
Can I just jump in real quick? I wanted to add something onto the prescribed fire question there.
Absolutely.
Just to say that, the Weather Service and all of NOAA really is working with our fire partners to provide site-specific forecasts so that they can determine what an adequate burn window would be when it's appropriate to be able to burn on the landscape in a safe manner so that it would not escape into a large wildfire. So that is kind of the role we're playing with our partners there, is providing those very localized site-specific forecasts so they can determine when they can safely reduce those fuels.
Thank you, Robyn. Thank you for jumping in there. I appreciate it. So I'm going to hop back to a question that was for Eric. Eric, what altitudes are covered by the HRRR vertically integrated smoke model?
Yeah, so the vertically integrated smoke is it's essentially an integral of the smoke through the entire atmosphere. And the top of the model is 50 millibars, I believe. So that's well into the stratosphere. And so any smoke within the troposphere will be captured within that product. Yeah. Good question.
Great, thank you. I'm going to hop back to the beginning with a question for Dan. The question was about logistics for people staffing fire incidents, and they were asking about camping out and about the tents in your pictures. If you could tell a little bit about the situation.
Honestly, you're prepared to be self-sufficient for 72 hours. The way that we didn't have a camping area set up this past week in Ennis, so I was sleeping in the back of a pickup truck for the first couple of days until we got the sleeping area arranged and things like that. So I pack a tent, I pack a sleeping bag, and whether it's the floor of a school, whether it's inside a rental vehicle, whether it's in a tent, whether it's in a truck, sometimes it even ends up being a hotel. We truly train and we're prepared to be completely self-sufficient for the first 72 hours until the logistics may catch up with the incident.
Great, thank you. I have a question that many of you can probably answer, and it's sort of directed to everyone. Where do you see the greatest need for social science research when it comes to fire weather?
I can start with that one, Asia. So it's really kind of twofold. We have a need for social science both within the wildland fire management community, which is historically where we've worked closely with our products and services, how they interpret some of those pieces of information, how and what they might need with regard to uncertainty and probability type of information going forward. And then, of course, there's the public piece of it, right? Because we do know that the public are using our products and services as well to make decisions. And so working with that community to determine what they need and what the appropriate service might be for the public. And it might be different than the current products and services that were historically developed for the wildland fire community.
Thank you. Does anyone else want to add answers to that question?
It's very important because the weather piece, as Robyn just alluded to, sometimes feels confined by our standard services. But as Brett alluded to, when you're dealing with an event like the Labor Day windstorm through the Pacific Northwest and the way that was going to move the fires, not only did it kill people in Oregon, but it also killed citizens in Northern California. Somehow the word has to get out that this is not normal, this is historic, and you need to make a decision now to protect your life, to protect your property, to protect your family. And that really only comes through some of the social science, social media stuff. It takes a lot of experience and a lot of hard work for the weather offices to come up with messaging that is so impactful that the public will really take direct action, because they get a lot of messages about the weather. And every once in a while, there's something combining weather and fire that they really need to respond to and be proactive.
Thank you. I have a question related to debris flow. Where can we find more information about the criteria or models used to determine areas at risk or of post-fire debris flow or flash flooding? Maybe that's Tony.
The best place to go is the U.S. Geological Survey's Landslide Hazards Group. They are the tip of the spear, so to speak, on the science behind debris flows, and they actually provide probabilistic debris flow estimates for most large fires in the West. So if you're looking for a place to start, that would be my recommendation.
Thank you, Tony. This one is for Brett and Dan. How is radar used while on site as an IMET?
Okay, well, I'm sure Dan has plenty to share on this, but there was some talk about pyrocumulus earlier, and that's one thing that we use the radar for. Basically, when you start to get radar returns from a fire, you know, you see the smoke particulate matter picked up by the radar, but then you start to see increased reflectivity when a pyrocumulus forms, and once a pyrocumulus forms, it's not always a sign of significant trouble, but it can be a precursor to a smoke plume that basically evolves into a convective cloud that starts to generate its own weather. You're looking for things like column collapse, potentially also fire tornado type activity like we saw on the Tenet fire in Northern California recently this year, and so that's part of it. You know, the other thing is we look for outflow boundaries. So basically using satellite and high resolution, you know, radar and satellite imagery is really pivotal to keeping firefighters safe when we're out there in the field.
Thank you so much, Brett. And with that, we're at time. I'm going to turn it back over to Kelly. I appreciate you guys all answering the questions and the wonderful questions that our audience posed. And Kelly, I'll hand it to you.
Thank you, Asia. Wow, the time goes quickly, doesn't it? That wraps today's 3-minute thesis webinar on NOAA's role in wildfire events. As we end, please hang tight for one more minute to answer a few brief questions that will appear on your screen. Your feedback is crucial to help us plan future webinars like this one. And I want to express my thanks to all of our wonderful panelists today, our coordinators, Bethany Perry and Asia Shumalo, as well as you, our audience. I hope you have learned something new and enjoyed these excellent presentations as much as I have. If you're interested in checking out past webinars, visit our website, noaa.gov/Central Region, where you will also find more great information. Thanks again for your participation. Have a fine day.